Okay, here we go. Number 6. So for this one, you guys are asking for me to take a look at part C. So in the first, I'm going to go through the first part really quickly. So you're driving forwards at a constant speed, but it's accelerating upwards. So you would need to have an upwards force of tension much bigger than your gravitational force going down. Okay, I'm not going to be super specific, but tension needs to be bigger than gravitational force. Okay. For part B, I'm going to use part B as kind of like a jump into part C. So if I write an equation for where my box is in the x direction, it's moving at a constant speed of 0.5 meters per second. So in the x direction, I can go like this. And in the x direction, where it is in the x direction is equal to, my acceleration is 0 because it's a constant velocity, so this is 0, plus the velocity in the x direction is 0.5 meters per second times time. And then I'm going to say that I started at a position of 0. So what I have left for the x direction to describe where it is 0.5 meters per second times time. All right, so that's the x direction. Then I can also do the y direction. In the y direction, my acceleration is 1 meter per second squared, and it's not moving up and down to start with. So I'm going to rewrite this equation, but do it for the y direction. Okay, and in the y direction, where it is in the y direction is equal to 1/2, and then my acceleration was 1 meter per second squared, and then times time squared, plus my starting velocity in the y was 0, so 0 times time is 0. My starting position in the y direction was 0, so that's just that. So that means that y is equal to 1/2 times 1, which is 1/2. My units are meters per second squared, and then it's times time squared. All right, so to do part B, then all I need to do is plug in the same amount of time. Like I could plug in 1 second for both of these. And then I can plot where it is in the x direction, where it is in the y direction. So in the x direction, if I plug in a 1, it's going to be at 0.5. And then in the y direction, if I plug in a 1, it's also going to be at 0.5. So then it'd be right there. And then if I plug in 2 seconds, then I get 2 times 0.5, which is 1 for the x. And 2 squared times 1/2 is 2. So then that would be here. And then does that make sense? So you just plug in the same time for both, and then you just graph it. So you're going to end up with a parabola that goes something like that. Now, what I'm going to do is I'm going to take these two equations that I just wrote, and I'm going to use them in part C. Okay, so what I'm going to do is I have two equations, and I need to get rid of time. So what I'm going to do is I'm going to take this one, and I'm going to get rid of time. I'm going to solve for time. Let's do it this way instead. All right, so I'm going to divide both sides by 0.5 meters per second. Now, because I want my units, I'm keeping my units in this mess. So x divided by 1/2 is 2. And then when I divide by meters per second, that's going to be the same as multiplying by seconds over meters. And then I'm going to still have my x. And then that's going to be equal to time. Now this, I can now plug in for time in my y equation. Okay, so y stays the same. 1/2 meters per second squared stays the same times. And then I'm going to put in parentheses this 2 seconds over meters times x. All of that's going to need to get squared. So that means I'm going to end up with 2 squared times seconds squared over meters squared times x squared, because I have to square everything. And what I'm going to be left with then, I can combine the 1/2 and the 2 squared, because that's 4 times 1/2, which is 2. So I have y is equal to 2 times, and I'm going to write out the units like this for a moment. Meters times seconds squared over seconds squared times meters squared times x squared. Okay, so then you'll see that in terms of units, the seconds cancel each other out. And in terms of meters, this meters is going to cancel out one of those meters. And so then I'm going to have left y is equal to 2 times 1 over meters times x squared. Now, this makes sense because when I put in a position of y, it's going to be in meters. And then if I put a position in for x, it's going to end up being meters squared. So if I multiply that times 1 over meters, then that's going to make sense. So then meters will be equal to 1 over meters times meters squared. So it does check out. It does make sense. 2x squared. Wait, what? Oh, for part B. So the way that I did part B, here, and I can keep going where I left off. So I'm going to plug in a time into each of my equations. So like I'm going to plug in now 3 seconds into this one and 3 seconds into that one. And so when I plug in 3 seconds, I get x is equal to 0.5 times 3. So that means x is 1.5. And at the same time, y is going to be equal to 1/2 times 3 squared. So y will be equal to 1/2 times 9, which is 4.5. And so then what I can do is when x is 1.5, which is here, y is going to be at 4.5. Yeah, you can use that as well. Either way, you can either do it with the 2 separate equations and just plug in the same time into both and see where they are and graph it. Or you can use the equation that we got in part C and then plug it into B. Other questions? Yes.
Can you just scroll back to the part C?
Yeah, of course. Anything else?